So this is the AP Stats 5.3 homework video on conditional probability and independence. You should be able to use the general multiplication rule and conditional probability formula to calculate probabilities and describe what independence means, quantify it, as well as describe what it means qualitatively. So let's look at an example problem to get started. Imagine flipping a coin 5 times. You get heads, then heads, then heads, then heads, and the 5th time, what's the probability of flipping again? So pause and think to yourself, what could that be? Well, in conditional probability terms, we'd be saying event A is that you flipped heads 4 times in a row on the first 4 flips, and event B is that you get heads on the 5th flip. So what's the probability of heads on the 5th flip, event B, given this vertical line, given that A has already occurred? We've already had 4 flips be heads. So if events are independent, then the probability of B given A will just be the same. It'll remain the same as the probability of B. That's what independence means. A conditional probability is saying, will the probability of this event change given that A has occurred? So when you read this, probability of B given event A, that means event A has already occurred. So in this case, they're independent because the probability of getting heads on the 5th flip is still 0.5. The fact that we got 4 flips before that are heads doesn't have anything to do with it. So in words, we'd say that one flip of the coin does not affect the next. So the probability remains the same. In probability notation, this is how we would write it. If we could write it the other way around, and that would mean that these two events are independent, meaning the probability of the event doesn't change given that something else has happened. So it remains at 0.5 for probability of B. If we looked at A, 4 heads in a row, that'd be 0.5 to the 4th. Another example is given down here about 2 separate rolls of a 6-sided die. Because they're not independent, like if a probability changes, it doesn't necessarily mean there's an association between them, but there could be. And the greater the probability is to change, the more that could be the case, meaning one event is associated with another. So take this opportunity to answer your FRQ, your free response, and I would look through the book at independence and some other examples. I would like you to explain in words, that'll be half the credit, using 1 to 2 sentences, no more, and then as well as probability notation, what it means for 2 events to be independent. So pause right now, answer the free response question, and then push play to continue for the multiple choice. So tree diagrams, we've talked about these briefly before, where it represents multiple outcomes, and our entire sample space could be represented on the far right here by looking at a series of outcomes, with this one representing heads and then heads, heads and then tails. Now notice the probability of tails is the same, even if knowing that I got heads on the first trial. That means flips of the coin are independent. Those probabilities remain at 1/2. So these tree diagrams become increasingly important, especially as it becomes more complicated and the probabilities of different outcomes change. They're not equal to, everything isn't 0.5. Then it becomes more complicated, and a tree diagram is a nice way to organize your work. So this can help us determine the sample space and the probability of each individual outcome, but also a series of outcomes, and it's a way to organize your thoughts. It's a nice way and organize your work as a way of showing work to determine a series of outcomes. So whenever we have a series of outcomes in some chance process, then think about writing a tree diagram to organize your work. Okay, let's look at the general multiplication rule. So we know for independent events, the probability of A times the probability of B is the probability of their intersection. That means that they both happen. Just think about like the intersection of a street. The intersection of Franklin and Eddy is where you're on both Franklin and Eddy. So that's the intersection. You're on both streets. The union would be on either street. So keep that in mind if you're still having trouble with the difference between an intersection and a union. This is where both circles meet in a Venn diagram. Now, if the events are not independent, then we'd find the probability of A times the probability of B given that A has occurred. So this means that the probability of B has changed due to A occurring. So these two events would not be independent. If they're independent, then that simply becomes, because the rule for independence is that this probability is equal to the probability of B happening, the formula will simplify to the intersection just being multiplying the two. So in the case of flipping coins, 0.5 times 0.5. In the case of pulling cards and looking at the first card's a heart, the second card's a heart, if A is the first card's a heart and B is the second card's a heart, given that we've already pulled a heart, my probability of pulling another one changes. It goes down from, I'd have 13 over 52 times 12 out of 51. So in that case, those two events are not independent. Another awesome trick in probability is to look at the complement rule. So I've mentioned this before, but we want to think, if you're ever asked at least one of something, think about the complement. So the complement to at least one is none, and that's oftentimes easier to calculate than calculating a series of outcomes. So 10 coin flips, probability of flipping at least one, you would have to calculate the probability of 2 plus 3 plus 4 plus 5 and so on. It becomes very complicated. So we can find the probability of 10 tails very easily. That's just one path on that tree diagram, 1/2 to the 10th. And then subtract that from 1 to find that about 99.9% of the time you'd flip at least one heads when flipping a coin, making it not plausible that you'd get, 10 tails in a row or 10 heads in a row. This is a really crucial part of the chapter, knowing the difference between mutually exclusive and independent. If two events are mutually exclusive, then they can't be independent. Why is that? Well, if they're mutually exclusive, then when one happens, the probability of the second one becomes 0. So that means they're not independent because the probability of that second event changed to 0. So by definition, mutually exclusive events are not independent, and independent events could not be mutually exclusive. So mutually exclusive events: A person is born male, B, a person is pregnant. They're mutually exclusive. A male can't be pregnant, and someone who is pregnant cannot be male. So if we know event A has occurred, that a person is male, then we know that they cannot get pregnant. So those two events are not independent because they're mutually exclusive. So the probability of event B becomes 0. The last piece of this video is calculating conditional probabilities. So this formula is what we're given, that the probability of event B occurring, given that A has already occurred, is given by the intersection of the two divided by the probability of A. Let's see why that is. Simple space for event A and event B, with the whole box representing every possible outcome and this representing A and B. These two events are not mutually exclusive because they have an intersection. Now let's just say we want to know the probability of B given that A has occurred. Well, A has occurred, so that means once A has happened, this represents all of our outcomes. A has already happened. So all of our outcomes following that are within this circle because we know that this event has occurred. So that represents the total possibilities for event B to occur. Of that green circle now, which is our total possibilities, this area represents the probability that event B occurs. So here's event A occurred. Of all those occurrences, this is where B happens as well. So this becomes our numerator, which is the intersection, and our denominator becomes the entire circle, the probability of A. So this is why that formula occurs. And that leads us to this formula: the probability of B given A equals the intersection divided by the probability of the event that's already occurred. For this event, for this to happen, A has to already happen, and then they both happen because B now occurs. Okay, your multiple choice is involving that conditional probability formula and this situation right here. Zoomed out a little bit. So given this Venn diagram, what's the probability of B given A? Here are your 5 possible answer choices. So now pause, go over the conditional probability formula in the 5-3 summary, look at those examples, and then answer the multiple choice.